All right, happy snow day, everybody. Snow day. So here's a quick part one video. I'm gonna have you watch two videos today. So if you can take a piece of paper and pencil and just kind of take some notes today so that you guys can get ready for what we're gonna learn when we come back. Okay, so first off, we want to start off with the first derivative review. And so if you can you take a moment to pause the video and just start filling out this chart right here? Okay, so pause and try to do some retrieval practice because that helps you remember and learn. So pause the video and give it a shot. Okay, so now that you've given it a shot, let's kind of see if we can answer these questions. So I'll start with actually this one is greater than 0. So if the first derivative is greater than 0, we know that the first derivative represents the slope. So that means the slope is greater than 0, meaning then that means the f graph must be increasing. Similarly, if the slope is less than 0, the f graph must be decreasing. Okay. All right, so let's go back to the top now. So now what if the slope graph, the slope is 0? What does that mean? Or is undefined at x equals a. That might mean that there is a critical number. You might remember something like a critical number at x equals a. Okay. What this means is if a slope is 0, we know that this is a horizontal tangent. And we know that horizontal tangents on a graph can look like, like this or like this. Both of these guys are horizontal tangents, which mean that this point at x equals a, it could be potentially a relative min or max. Okay, potentially. And I say potentially because don't we also have graphs that go like this and then flatten out and then go back up? Right here is also a relative, a tangent, horizontal tangent 0. Okay, but that's not, this part is not a relative min or max. All right, so the final two. What if our slope, the f prime graph, changes from positive to negative? Doesn't it look like this? Positive to negative. So that must mean there is a positive to negative slope. Must mean that right here there is a relative max. And finally, if you change from negative to positive, at that point it's a relative minimum. Okay, it's awesome. So let's try to see if we can apply this. Here's this graph of f, x cubed minus 3x squared. We want to find when the intervals for increasing, decreasing, and any relative min or max coordinate pairs. Okay, so what we first do is to find any of this information right here, we need to look for information using the f prime function. Okay, so let's first find the derivative. The derivative is 3x squared minus 6x. Okay, so now looking at the chart above, we know that it's increasing when the derivative is greater than 0, so or less than 0. So let's first set this equal to 0 to find our critical number. Critical numbers happen when the derivative is equal to 0 or undefined, does not exist. So let's set this equal to 0 for now because it can't be undefined. 3x squared minus 6x is equal to 0. We can factor out a 3x, so we get x minus 2 is equal to 0, and that leaves us with x is equal to 0 or 2. These are the critical numbers. Okay, now critical numbers tells us it might potentially have a relative min or max. We got to figure that out. So if you remember, we make a chart. Here's my chart of my x values. Here's 0, here's 2. These are my x values. Okay, so now we want to figure out, all right, what does my f prime look like at this moment? So I want to plug in a number that's somewhere right here, maybe a number right here and a number right here. So a number to test might be -1. A test number here might be 1, and a test number here might be 3. Okay, so I'm going to test those. If I plug in -1 into my derivative graph, so f prime of -1 is going to equal 3 times -1 squared minus 6 times -1. What does that end up becoming? That ends up becoming positive 3 plus 6, which is a big number greater than 0. So we know that all these numbers right here are going to be positive in this zone, right? Greater than 0. Let's do f prime of 1. 3 times 1 squared minus 6 times 1 is going to be 3 minus 6, which is less than 0. So I know in this zone, it's all going to be negative numbers for my derivative. Finally, I can do one more. My third test would be 3 times 3 squared minus 6 times 3. That's going to equal 27 minus 18, and that is greater than 0, so these are going to be positive. Okay, so I think we're all set. Let's use our chart to help us out here. Okay, so when we're talking about intervals for increasing happens when, in this zone, when the slope is greater than 0. So where is my slope greater than 0? Here's my slope. Greater than 0 is in those intervals. So I can say the increasing intervals are from -infinity to 0, union 2 to infinity. And again, that's here, this zone. From -infinity all the way to 0, and then from 2 all the way to infinity. Okay? So let's do our decreasing now. So decreasing is going to happen in this zone right here. Decreasing is when the derivative is less than 0. So that's going to be from 0 to 2, and that's it. Okay, finally, let's do our relative min and max. So relative max, relative min. Our relative max occurs right there when the slope changes from positive to negative, and that occurs right here. Do you see how it changes from positive to negative? So at x equals 0, that is our relative max. Our relative min would be when the slope changes from negative to positive. So from negative to positive happens right here at x equals 2. Done with that. Okay, so I believe it says find the coordinate pairs, so let's actually do that. So if we know x equals 0 and x equals 2, how do we find the y values? Do I plug it into right there, my derivative, or do I plug it into my original function? Well, we know that to find y values, we plug it into the function. To find slope values, we plug it into our derivative. Okay? So we plug it into our f. So if x equals 0, f of 0 is going to equal 0 cubed minus 3 times 0 squared, which is equal to 0. So the relative max is actually going to have a coordinate pair of 0, 0. And my relative min is going to be f of 2, which is going to be 2 cubed minus 3 times 2 squared, which is going to equal to 8 minus 12, I believe. So that is equal to negative 4. And then we need to do the coordinate pair. So this is 0, comma, no, sorry, 2, comma, negative 4. So this would be our solution to this problem. All right, so now we want to introduce the second derivative right here, okay? These are the answers that we came up with last time. I just put it in a neater form. And we know that the first derivative gives us all this information, right? But I'm letting you know now that the second derivative also gives us information too. And you can see a lot of similarities for when the second derivative is positive, when the second derivative is less than 0, when the second derivative is equal to 0, or when it changes signs, right? Those things all tell us information about the f graph as well. Okay, we're going to explore that. So we're going to first focus on this guy right here. Okay, so if I know that, just review, the first derivative is basically the slope of f, right? So it tells me how f changes. Then we can say that the second derivative is the slope of f prime, or it can tell me how f prime changes, or in other words, how the slope changes. So check this out. If we are trying to figure out how the slope changes is positive, then what we're saying is if we have different slope values, here's slope of 1, here, oh, maybe I should say it this way. Here's a slope of 1, here's a slope of 0, here's a slope of negative 1, here's a slope of negative 2, here's a slope of positive 2. Okay, so if we want to figure out how the second derivative is positive, what this really means is how the slope changes to be more positive. Okay, more positive. So basically we want to order it from least to greatest. Okay, so what's the smallest slope? Negative 2, right? Then what's my next one? Negative 1. Or maybe I'll do it like this. Then what's the next one after that? 0. You see how I'm getting, my slope is changing to be more positive, right? I'm going from negative 2, negative 1, 0. It's getting bigger and bigger. And finally, the biggest one. Now, what do you notice if I draw a little thing going through all of this? Don't you see that there is this behavior when my slope changes from being negative to more positive at the end? This is what we call concave up. Pretty neat. So up here, I'm going to fill out my chart. Whenever my second derivative is greater than 0, I know it's concave up. Therefore, you couldn't assume that if it's less than 0, it's going to be concave down. Okay, so now when it equals 0 or undefined at x equals a, so what if the, so what we say is it has a potential inflection point. Okay. Now what is an inflection point? An inflection point looks like this. Okay, let's say this is a function. It says the inflection point is when it changes from positive to negative, right? When the second derivative changes from positive to negative. So what we're saying is, what was it when the second derivative is positive? Isn't this concave up? And if the second derivative is negative, we said it's concave down. Okay, maybe I'll change the color here. Concave up, concave down. Okay, so where is it concave up on this curve? Isn't it right here? Concave up, right? And then where's it concave down? Concave down, concave down. So the point where it changes is right here. This point, this point, this point. All three of those points are the inflection points. So whenever we have a change in concavity, either of these, we call all of these inflection points.